The weight of the fluid displaced. Archimedes determined that the weight of the water displaced by an object is the key to floating. We can measure this by first weighing an empty container for catching water. We'll need this for later. Now, gently drop an object, like this child's bowling ball, into the fluid and be careful not to spill any. As you know, the water level rises because it's being displaced. Using this fancy piece of equipment called an overflow container.
You mean a bucket with a hole in it?
Yes. We can catch all of the fluid that's pushed out of the spout, down to the last drop. Finding the displaced fluid now is just a matter of reading the scale. One problem though, the scale is reading the water, but it's also measuring the bucket. This is why we measured it empty by itself first. We only want to know the weight of the fluid displaced, so we subtract off the weight of the bucket. The weight of the water pushed aside by the bowling ball will help us understand why it floats. Now we know about weight, fluid, displacement, and a little density too. On to the final hurdle in understanding Archimedes' Principle.
Buoyant Force.
A force is a push or a pull. As you sit and watch this program, there are forces acting on you. Gravity pulls us down towards the center of Earth, and the chair supports us with an upward force. And without this upward force, you would fall to the floor. Notice that the forces are the same size. We say that the forces are balanced. It's like a constant game of tug of war. If the forces are balanced, then the rope won't move in either direction. When one team pulls harder than the other, the forces become unbalanced. Only then does the rope move. In fluids, there's a battle between forces as well. Gravity forces downward, but without another force to balance it, everything would sink. We need an upward force to work against gravity and keep things afloat. This is called a buoyant force.
So the weight of this object comes into play. Okay, so that's the first part of Archimedes' Principle, a weight of an object. So it's the weight of this object. Why is it important? Because the weight is related to how much gravity is pulling down. That's a force. That's the downward force. The upward force is the buoyancy force. And what the buoyancy force is, it's all the pressure that's acting on the bottom of this vessel, pushing it up.
Let's prove there's a buoyant force by weighing a brick. As any object is lowered into the water, it gets lighter. The water is forcing up on the brick and cancels out some of its weight. This is the buoyant force in action. But even though it's lighter, it's not light enough to overcome gravity. The brick sinks. So where does a buoyant force come from? Just like your chair holds you up, fluids have the ability to force back on the matter that's sitting on top of it. Consider some water along this line near the surface. Water and air force down on this point just like when you sit in a chair. The water at this level must push back with the same force. As we go deeper, there's greater weight sitting on the water. So the water at this level has to push back with equally greater forces. See how the forces get larger the deeper we travel? The Uss North Carolina. Finished in 1940, it was the first of many modern battleships. Longer than 2.5 football fields from aft to stern and over 100 feet wide, this seasoned battleship was a key player in the war against Japan. Primarily built from concrete, steel, and wood, the North Carolina housed over 57 guns, a seaplane, and more than 2,000 sailors. Fully loaded with fuel and water for its boilers, the North Carolina weighed in at a staggering 46,000 tons. The massive weight of this battleship would be a significant force downward on the water. And the forces near the surface of the water would not be enough to hold up a ship of this size. This is why we never see battleships floating like styrofoam on top of the water. The boat will sink until an equal force can hold it up.
What will happen is, if an object is heavier, more fluid must be displaced, and typically that means the object will have to go deeper in the water.
The North Carolina displaces 46,000 tons worth of water in order to float. Now, a lighter object like this 4,000-pound seaplane will only have to push aside 4,000 pounds of water in order to float. Make sure you see the relationship. As an object displaces more water, it has a greater buoyant force acting on it. Archimedes' principle states that the weight of a fluid displaced will equal the buoyant force on an object. The following demonstration is used to prove this principle to be true. Remember the brick from before. It had a buoyant force of 7 newtons. We calculated that by looking at the difference in its weight above and below the water. Now let's do the same experiment, but this time catch all of the displaced water. Look, the brick pushes out 7 newtons of water. Archimedes' principle is correct. The weight of the water displaced equals the buoyant force on the brick. Archimedes' principle says that in order to float, an object must displace an amount of fluid equal to its own weight. A ball of clay doesn't displace enough water to float, but watch as these students transform the clay into a shape that can sit deeper in the water. Oops, not enough water was displaced that time. Ah, much better. These boats are deep enough in the water to float. Shape is everything. As we have seen, even concrete and steel can be shaped into a floating battleship. Think of it this way. When a hippo pushes water aside, which is heavier, the hippo or the water? The force of the hippo down is greater than the water pushing up, so the hippo sinks. A fish should displace water equal to its weight in order to hover within the water where it chooses. And the Uss North Carolina is obviously not completely underwater, but the water that is displaced must weigh the same as the ship. Which of these barges on the Mississippi River has more cargo on board? We can tell just by looking at them. The heavier barge is the one deeper in the water. Heavier objects must displace more fluid to get a bigger buoyant force. When a boat takes on more weight, it lowers into the water. Eventually, the ship runs out of hull and starts to take on water. This water adds more weight. In order to stay afloat now, the ship must sink deeper into the water, which lets in more water, which adds more weight. So the ship lowers into the water and takes on more water weight. The physics of sinking are hard to overcome once the cycle has begun. Now, some canoes have styrofoam in their tips, which makes it very difficult to sink. These boats can still stay afloat even when filled with water and people. Swamping a canoe can be a lot of fun, but it isn't very easy to paddle.
Now here's kind of interesting. When you and I stand on a bathroom scale, depending on how big we are and how much, there is a buoyancy force associated with the atmosphere. We are displacing air.
So just by being here, you have a buoyant force equal to the weight of the air you push aside. Obviously, no human has a buoyant force large enough to fight off gravity and float, but a hot air balloon does. A balloon must displace cold air to rise. It must move aside more cold air than the basket, people, fuel, material, and the hot air inside it.
So how do these things fly?
How do they fly? They fly by basically having hot air. Hot air goes into the balloon and it rises. The more you heat up the balloon, the more it wants to rise.
The pilots warm the air in the balloon with fire. As the hot air spreads out, it becomes less dense. Some air is pushed outside of the balloon, and less air means less weight.
The envelope itself weighs about 350. The basket fully loaded with fuel is about 450, 475.
When the balloon, basket, people, and fuel are added, the total is still less than the cold air that was displaced. And away they go, buoyant forces winning out over the force of gravity. Gently gliding where the winds take them on a beautiful summer afternoon. It's too bad Archimedes never had the opportunity to witness his principle take to the skies.
Eureka!